Hi, everyone. As Sam said, I'm going to be talking about how can we assess and anticipate the behavior and knowledge quality of large language models for clinical applications. I am an assistant professor of radiation oncology at Brigham and Women's Hospital in Dana-Farber, and I'm also part of the AI in Medicine program at Mass General Brigham, where I lead a lab focused on natural language processing applications, primarily for cancer care. And now we're doing uh, 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 quite a bit of work in language model evaluation methods. Here are my disclosures. So today, I'm first going to start with a brief introduction to why it is so difficult to understand and predict the behaviors of large language models generally, and specifically in medicine, and highlight some of the gaps that hopefully over the coming years we'll be able to start to fill in developing methods to understand to gain a stronger understanding of the foundational knowledge of large language models for clinical medicine and therefore what the best way to apply them are. And then I will go into some of my group's work into assessing the quality of language models for clinical reasoning applications, both from the top down, kind of starting with a task and evaluating how the language model performs in that task, and from the bottom up, which is our attempts to try and anticipate language model behavior and risks from details of its pre-training data and potentially its architecture. And finally, I'll touch on what I think is really the boots on the ground hardest part of language model uh, application in clinical medicine, which is how do we actually evaluate these in a way that is preclinically robust enough that we can feel comfortable moving them into clinical settings. So over the past few years, there's really been an exponential kind of rise in the performance of large language models on general biomedical tasks. So back in 2018, the kind of first generation of what now led to the large language models came out and became popular in the field of NLP. Those were language models that use contextual embeddings with an attention mechanism. I'm not going to go into the technical details of all of that. But the first models that really gained traction, it was a series of models that came out of what's called a BERT model that Google developed in 2018. And the BERT models beat the state of the art in a lot of established NLP tasks in ways that were really quite astounding. And back in those days, we would consider those were considered very large models, but they were on the order of tens to hundreds of million of parameters. Since then, models have been trained on progressively more data and with bigger architectures and with more compute power, leading us to today's generative large language models. They also have a slightly different architecture than the original BERT models. They have a decoder-only architecture. They're trained to simply to predict the next word in a sentence. So you're able to kind of get free supervised, semi-supervised training from huge amounts of internet text because you simply just need to have the model predict the next word in a sentence. These new classes of large language models are more on the order of billions of parameters. And what we saw in 2022 when OpenAI released their GPT 3.5 models was that suddenly language models were able to pass the medical licensing boards, the USMLE exam. It's also called the MedQA benchmark in NLP. And this was really, truly amazing. If you had asked me in August of 2022 whether we would be about to see um, language models being able to do decently well on the USMLE board exams without any task-specific fine-tuning, I would have thought that we are nowhere near a world where that would be possible. So that in itself was quite impressive. And then since then, models have been refined. Some are larger, some have have various different approaches to prompting the models. And now many of the state-of-the-art large language models are able to do very well in the USMLE board exams. And from that, we got a series of papers kind of claiming that large language models are clinical reasoners. Similarly, these models are able to perform well in other benchmark data sets in the biomedical realm outside of simply the USMLE medical licensing board exams. And what is the really key exciting feature here is the fact that the models, as I said, do not need task-specific fine-tuning. They don't need to be fine-tuned to answer questions about the biomedical boards to be able to to do well in the biomedical boards. They learn enough information about the biomedical domain in their pre-training and being pre-trained to predict the next word in a sentence on huge amounts of data to be able to pass the boards. And that's some people refer to that as an emergent quality and something we really only started to see in models in the kind of starting in the tens of billions of parameters and up range. So these large language models clearly learn some general biomedical knowledge, which we can measure on multi-choice QA exams, essentially. However, being able to pass a multi-choice question answering test does not make a clinician. So how does that translate into real improvements or and support for healthcare applications? And this is what I believe to be one of the most important unanswered questions that we as a community need to solve with respect to large language models for effective and safe clinical translation is how do we anticipate and measure the performance of large language models and their safety risks in unseen circumstances, which our current benchmark evaluations are not able to provide. And that's what I'm going to kind of discuss in more detail throughout most of the talk today. And we can take a top-down or bottom-up approach to this. We can still choose a task that we might want a large language model to do. So we're kind of, if you start with a hypothesis, I think a large language model would be good at answering patient questions in the patient portal. You can create a crafted data set for that task and evaluate its performance on that specific task. However, with that type of approach, you don't know if that's going to extend beyond the extent to which what your findings will extend beyond your data set you've developed and certainly not beyond the task you developed. So it's limited and not a super scalable approach. However, that's the current standard approach. The bottom-up approach is trying to learn from how the model is trained, from the model's architecture, whether that can tell us that usable and useful information about a language model's behavior and knowledge with medicine, which if we're able to achieve that would be a more scalable and reliable approach to evaluation. And this all comes down to the pathway from how we get from data to knowledge. So data is provided context and meaning and becomes information. And knowledge implies an ability to use that information to and apply it to new behaviors and to new domains. And so the top-down approach is really focusing on what is a language model knowledge and can we learn something about the truer details of how that model arrived at the knowledge just from studying the end knowledge? The bottom-up approach is the vice versa. Can we learn something from about the model's pre-training data and how it represents that data to tell us something usable and generalizable about the model's downstream knowledge for a given domain? And for, basically in parallel with the large language models coming out, becoming very popular, getting a lot of hype, studies started to see that there were false or surprising features of how large language models reason or manipulate knowledge, which complicate how our ability to evaluate their knowledge quality. So the most well-known of these kind of faulty knowledge manipulation phenomena is the reversal curse, which is that models may not be able to answer a question in direction A to B, but not B to A. So this is an example of that. So if you ask many of the the state-of-the-art large language models, who is Tom Cruise's mother, they will correctly respond, Tom Cruise's mother is Mary Lee Pfeiffer. However, if you reverse that question in a way that kind of implies the same knowledge base, who is Mary Lee Pfeiffer's son, the models often are unable to answer the question in the opposite direction. So even though they're able in the first setting to reliably extract the knowledge, and this is in the A to B, who's Tom Cruise's mother, Tom Cruise's mother is Mary Lee Pfeiffer, is probably more reflective of like how a Wikipedia page might describe these two facts about who Tom Cruise is and who Mary Lee Pfeiffer is than the opposite form. It cannot manipulate that in the way that we would assume that a human would be able to manipulate that. Similarly, another common challenge is that even though models may be able to accurately extract information, it can't tell you something logical about take the next step to answer that would require knowledge manipulation to make for logical queries. So the example of this is a model may know that the dates that Joe Biden and Nancy Pelosi were born and be able to reliably tell you that Joe Biden was born in 1942 while Nancy Pelosi was born in 1940. However, if you ask it to kind of take the next step and manipulate that information but tell you who was born earlier, it might get that wrong. So information memorization and knowledge extraction doesn't imply comprehension. You need both. And models don't learn and reason the same way as humans do. So we can't necessarily say, because a model is able to answer this one set of questions that we believe is representative of that domain, it will be able to then manipulate and generalize that information to other similar tasks in the same way we might be able to assume a human could do. And the way we, in fact, do assume humans do when we use board exams and standardized testing to assess competency. Okay. So now drilling down into the top-down approach to understanding model behavior. And as I said, it's very hard to anticipate language model behavior and what a large language model truly knows. So this is the figure that I showed a few slides back showing how many of the large language models perform very well on a range of biomedical related question answering tasks, including USMLE, the USMLE medical board exam, which is also called MedQA, and another standardized test for medical knowledge, or multi-choice question answer test for medical knowledge called Med Multi-Choice QA. These two benchmark data sets are commonly used in the NLP community to demonstrate clinical reasoning behavior. So we wanted to dig into whether a language model's performance on those benchmarks is really telling us something true and usable about the model's knowledge and ability to manipulate information with respect to those domains, or is it simply telling us something very narrow about those benchmark data sets? And so we took a very simple approach. Many of these questions, because they're medical board examination type questions, include mentions of medications in the either the question stem or in the answers. And so our kind of starting hypothesis was that if a language model is able to correctly answer a multi-choice question answer that has a medical term in it, and it is able to match the brand and generic names of that same drug, it should always answer the question the right way, no matter if you insert the brand name or the generic name of that drug in. If it truly understands and is really, if answering that question is telling you something about the underlying understanding of the knowledge base. So we took the two benchmark data sets, extracted all mentions of medications, swapped the brand and generic terms of those medications to create two paired data sets, one with the generic terms, one with the brand terms. And then we did some human verification to make sure that the swapping the names and context didn't alter the meaning of the question. And we wanted to see how well how similarly the model performed on the two paired data sets. Again, ideally, if the models know that the brand generic names refer to the same drug, they should always answer a question about that drug the same way, regardless of what regardless of what name is being used, as long as the question isn't specifically asking, is this name a brand or generic term? So first, we of course had to test how well models are able to do that first step of simply matching the brand, the generic names as being the same. And for most of the larger state-of-the-art language models, kind of looking at the mixtral and above family of models. These are the models we assessed ranked by model size. They do very well at matching the brand generic drugs, especially starting at the llama 73 billion range. They're nearly perfect. So this actually is really impressive. I couldn't do this well at matching brand generic terms, and again highlights that now that these models do memorize a lot of information that can be extracted. So that knowledge extraction for brand generic information is intact for many of the larger models, not for the very small models. However, when we posed the swapped question answer data sets to those same models, we saw quite a bit of variability in the performance in the accuracy of the models between the brand version of the data set and the generic version of the data set. So on the left is the Med multi-choice QA benchmark accuracy difference. So ideally, there'd be no difference between the generic data set and the brand data set. So ideally, there'd be no bar, but you can see most of the models demonstrate variability on the order of about a 5 to 10% change in accuracy. MedQA also showed quite a bit of variability, although if you notice here, the x-axis scale is narrower, so we're not quite as much variability as we saw with Med multi-choice QA. But just to highlight one very popular model, which is Llama 370 billion. So this is not quite as large as the proprietary family of models, but it's probably one of the best open source models. This showed a lot of variability in the performance on Med multi-choice QA, a 10% performance change just by swapping the brand and generic terms. Where despite the fact that these models did a very good job at knowing that the brand and generic drugs were the same. So what does this tell us? First, it tells us that language models are not robust to lexical variations. So they don't handle the lexical variations in drug names once you get to higher order reasoning tasks, even though they can do the simple name matching very well. We did try making this task really easy for the model. So we would give the we would give the question stem along with a key saying this is the brand or generic name of that drug that's in the question stem to kind of give them the answer and see if that solved the problem, because that would be a simple solution for this one narrow task. That actually didn't solve the problem. We still saw variability, so it didn't handle that extra information provided in context very well. So why might this be? One is data set contamination, which is the issue of, are the models really memorizing? And is the performance telling us something about the model's ability to memorize, or is it telling us something true about the model's knowledge quality in clinical medicine? So we looked at a publicly available pre-training data set just to try and get a sense of how much these data sets that the models are trained on, and therefore, could quote unquote cheat because they saw the answer in their pre-training. How often these data sets show up in the pre-training in the internet and common internet pre-training data sets. And you can see for MedQA, it was a huge amount of contamination. All of the splits were very highly contaminated in a common pre-training corpus. The test with 99%, the test data set, which is the data set used to evaluate performance, was almost completely contaminated in pre-training. There was less contamination with Med multi-choice QA. Potentially, this might explain why we saw more variation in Med multi-choice QA and might point to one solution for this robustness challenge. Maybe just seeing so many examples of the similar questions in the pre-training data help kind of reinforce memorization in a way that supported knowledge from MedQA, or it just made the task so much easier for the model. And, the model was able to see the answer, in which case this is not really generalized to anything at all usable. And, it's important to know, especially with brand and generic terms, there are probably biases and imbalances in where brand versus generic names show up in relation to other words in the general internet. Brand names are likely to show up in advertisements, whereas generic names are more likely to show up in scientific publications, for example. And, models learn information from the terms that are proximal and contextually relevant for where a single token in question shows up. So there probably are learning biased knowledge representations that are for the brand generic names that are slightly different from each other, leading them to answer questions differently. So what are the immediate ramifications? The first immediate ramification is these common benchmark data sets are contaminated in the pre-training data sets, which is really limits their usability period. And even if they were not, this robustness really presents a challenge and tells us that these simple question answer data sets might not really be telling us about the general knowledge capabilities, and certainly not the knowledge manipulation capabilities that we might assume it's telling us if we're kind of anthropomorphizing the models, what we would assume a human doing well on those benchmark data sets would be telling us. For the drug task, other ramifications include, issues with misinformation, prescription errors, and biases about preferencing one drug over the brand over generic or vice versa. But from in a broader sense, we looked at drugs as kind of an easy to access use case, but lexical variations and synonyms and abbreviations and typos are very, very common throughout the biomedical literature and especially common in clinical documentation. So if language models are not able to effectively and reliably handle all of these variations in a similar manner, that's a real safety risk and makes it difficult to truly evaluate because it's hard to capture all of that linguistic variation that appears in medicine in a single evaluation data set. So there are some potential solutions to this. From the engineering side, we can improve pre-training data and approaches. There are emerging ideas for how you can mix in, different ordering of questions to help solidify and make those models more robust to lexical variations and make them better at handling knowledge manipulation. We can, of course, take the large language model and fine-tune it for our specialized task with labeled data. Fine-tuning is a way that you can, improve the performance of your model for your specialized task, but you might potentially lose the generalizability of the large language models that people really like for the language models. And we can, of course, refine in-context learning approaches. Our one solution of basically giving the brand generic terms in context might not be the best solution to solve this one particular challenge, but that's not a scalable solution. And then from the clinical researcher aspect, I think this does really point to the need for a better and more clinically relevant data set to evaluate large language models against. The NLP community is using the benchmark data sets that enable automated assessments. So those question answers, you can automatically calculate accuracy, but those are not reflective of true clinical tasks that are especially not reflective of the open-ended generative type tasks like creating like dialogue, like writing responses to a patient question, like creating a document. And there are nearly zero benchmark data sets reflecting those more clinically relevant use cases that people are excited about using large language models for. And then ongoing end user education and monitoring for any safety risk as we evaluate them, any challenges to robustness. However, that being said, we can't always rely on the human in the loop because there is automation bias and over-reliance when humans and machines interact with each other. And I'll come to that in a little bit, come back to that in a little bit. Okay. So that's one bottom-down approach where we kind of looked the common question answer benchmark data sets as our task and try to find where there might be holes and challenges that we can start in language models, knowledge capabilities that could point the way towards what we need to monitor for in any clinical implementation and where we need more research to fill those gaps. However, they're not scalable because of the very large output space and general nature of large language models. So, if you were to take only a bottom-down approach, you need to study performance and risks individually across many different tasks, all different syntactic variations of this same content, study it across languages, etc. So it's really a scalability challenge. If there are a way to anticipate language model knowledge and behavior upfront, that might be a more scalable and reliable solution as people extend large language models to open-ended type tasks. And that is the idea of assessing a large language model's knowledge from the bottom up. How do language models learn what they know? And what might be flawed in that process. So this is work that was led by Sean Chen and Jack Galiphant, a grad student and postdoc in my lab, where we wanted to take the bottom-up approach to understand how language models might be learning biased understanding of disease prevalence across demographic groups. And this was motivated by multiple prior studies that showed that if you have a large language model just generate medical content about patients or respond to patient questions, they will insert diagnoses in a biased fashion. So we know that there are some incorrect and biased associations between within a language model between demographic subgroups and how likely that subgroup is to have a disease. That is then reflected in their output space. So our cross-care project was trying to understand how a large language model might be learning that specific type of bias and to assess assess one potential approach to understanding how models learn their knowledge representation. And that approach is comparing how often does your concept of interest appears in your pre-training data, how that kind of statistic is reflective or not reflective of the large language model's final knowledge, and how that compares to the real knowledge that you would ideally want your large language model to achieve. So I know that's very vague and specific. For this project, we were interested in 3 sources of disease prevalence ranking. Well, I'll say quote unquote information, because some of it's not real information, some of it's proxies for information. And so what disease prevalence ranking across demographic subgroups is the ranking of the most of the demographic subgroup. We looked at both race, ethnicity, and gender from most to least likely to have that disease. So the output that kind of for all of our information sources, we wanted to gather what we thought is most likely represented in terms of the most to least prevalent, likely demographic group to have a given disease. So for pre-training data, we calculated this knowledge source by quantifying the co-occurrences of demographic terms and diseases in a common pre-training data set. This data set is called the pile. So we took all the documents in the pile data set, and we counted how often our terms reflecting our disease of interest appeared in proximity to a gender or race mention. So for example, you might have a text that says for Asian postmenopausal woman with estrogen receptor positive advanced breast cancer, In this sentence, because breast cancer shows up in proximity to Asian, that would count as one co-occurrence for the demographic group. And because breast cancer shows up in proximity to women, that would show up as one be counted as one co-occurrence for the female subgroup. And we looked at various windows to assess this over a span ranging from 50 to 250 tokens or approximately words. And it didn't really change our results. So I think the results I'm showing here are all for the 250 word windows that we use to count co-occurrences. If those two terms showed up within 250 words, that was a co-occurrence. So we counted those co-occurrences and we used that and then we ranked which demographic subgroups had the most to least co-occurrences in the piled data set. For large language model knowledge, this is the hardest knowledge source to really quantify because we don't, the real foundational issue is we don't have a very reliable way right now to say this is definitely what a large language model knows. So our initial thought when we were going to try and query a large language model knowledge for disease rankings for demographic subgroup rankings for a given disease was to just ask the language model to spit out the ranking, the demographic ranking, or to provide for each demographic subgroup an estimate of the prevalence in the United States. However, that's problematic because we know that large language models will always, well, they often want to give an answer that they really want to give an answer, and it may not be the right answer, and it may not be what it actually thinks to be the most likely answer. And since we don't currently have the technology to effectively elicit what the language model really thinks is the right model approach, we couldn't use those to approach those kind of our initial ideas because it was not reliable. The models could just be lying to us, essentially. So instead, we use the logits of the model. So a logit is a raw output score from the final layer of the large language model, and it's representative of the language model's prediction probability or preference for each potential output. So how this ends up looking is we created templates that we thought would be likely to elicit the language model's preference for what demographic subgroup is most likely to have a given disease. So we had templates that look like this. In America, disease X patients are usually demographic groups Y. So then we populated it with our diseases of interest in our demographic subgroup. So in America, breast cancer patients are usually Asian, and then we calculate the logit value for this last token being as Asian, and we use that to calculate the ranks. Since as I previously discussed, models are not robust and they will often give different answers despite even very small variations in how you pose how you provide the prompt, variations in the actual prompt. We created 10 different variations of a similar prompt like this, and to assess kind of how stable our findings truly are. And our results were fairly stable over the 10 template variations, but this is one limitation of the study. We can't scope all the ways that you could probe this. And then for our real knowledge, we use the CDC statistics for 15 diseases. And that was the best quality information, true information source for disease prevalence across demographic subgroups that we could find. And then we compared the ranking of disease prevalence across our demographic subgroups using the above three sources. So our desired scenario is that the rankings would be the same for the pre-training data, the large language model knowledge, and the real knowledge. This is what you would ideally want to have a model that correctly learns the correct information from its pre-training data in the right way. And any variations therein might tell us something about how the language model might be learning incorrect information. So these graphs show the agreement in rankings for gender and for race over two models that are pre-trained only on the piled data set. One's called Pythia, the other's Mamba. Mamba, for those who are working on large language models, is not an autoregressive language model like it has a different architecture, but because it was only trained on the pile, we wanted to assess it as well. And on the x-axis is version of the same model of increasing size, ranging from a few million to billions of parameters. The y-axis is the Kendall-Tau agreement metric. So Kendall's tau, where -1 is a perfect disagreement in rank, 0 is random, and 1 is perfect rank agreement. And so ideally, we want all of our lines to be at 1 across all the model sizes. But in reality, what we saw was that, as shown in the green and blue lines, um, the green and blue are showing the same thing, except one is using a broader set of diseases that we had less high quality demographic groups for. Um, these are showing the agreement between the pre-training co-occurrence rankings and the model knowledge. So these are close to 1. They agree quite well with each other, especially for smaller models for gender. And then for race, it was a little bit invariant to how big the model was, but with more than 0.5 in almost all the cases. So this tells us that it does seem that the how often the terms co-occur in their pre-training data impacts the model's ultimate understanding of disease prevalence across subgroups, at least in our approach to estimating that. And for gender, it does look like smaller models are more reliant on those simple co-occurrences than larger models. When we compared the real CDC statistics rankings with our model knowledge rankings, which is the red line, these were closer to 0. So the model knowledge is not reflective of the true distribution of disease and demographic subgroups in the United States. So this tells us that large language models learn preferences from pre-training data co-occurrences, and that pre-training data and language model knowledge is not reflective of real disease prevalence. And the latter we did kind of already know, but it confirmed that. So Pythia and Mamba are good models, but they're not the state-of-the-art large language models that you hear people talking about all the time, and they're a lot smaller. We use those two models because they're pre-trained only on the pile, so we could say we know exactly the co-occurrence data for the exact model that was pre-trained on it, whereas the larger models tend to not make their pre-training data sets publicly available. But we wanted to see whether, if we took the pile as an estimate of kind of maybe potentially similar to other pre-training corpora, how do our statistics compare when we're looking at one of the bigger state-of-the-art language models? So we looked at Llama 3 for these each on these shows all of our 15 diseases that we had the best quality gold standard data for from the CDC, and the rankings for the pile data, the pre-training data in blue, the language model knowledge rankings in green, and the real statistics in red. And the real takeaway here is just that ideally you want all of those those dots of 3 colors to line up perfectly, but they don't, and they almost never do. Telling us that Llama 3, which again, a state-of-the-art model that you would assume probably has better understanding of disease prevalence across subgroups than the smaller Pythia models, still, doesn't isn't reflective of the real kind of demographic distribution of diseases. Finally, one way that is commonly used to align models with kind of preferences and potentially make a safer model are various alignment strategies. And these are things like reinforcement learning with human feedback or various preference optimization models that are sometimes being touted as ways to make the model safer and more reliable. We wanted to simply see how these alignment strategies impact models, the language models, what the language model knows about disease prevalence across subgroups, whether it impacts it at all. And we also wanted to see whether if you ask the question in different languages, does that elicit different knowledge from the model about demographic subgroups? So We rewrote our prompts into Chinese, English, French, and Spanish. And for each of the settings, we compared a base model here at Llama 2 with a reinforcement learning with human feedback fine-tuned model, which is how the GPT series of models from OpenAI are aligned versus a biomedically tuned model versus a supervised fine-tuned model versus a preference optimization model. And what we found here was that if you look in English, the most likely race to have a disease overall did shift when you asked in English over the different alignment strategies. But it shifted a lot less when you ask in Chinese, French, or Spanish. So the alignment strategies do seem to alter knowledge representation, but only in English. And that's probably primarily in English. And that's probably because the preference tuning data sets are primarily in English. We did see some shifts in Chinese as well. So alignment strategies don't totally correct language model preferences towards more accurate reflections of real world prevalences. So despite being one attempt to make a safer model doesn't make it a more accurate model. And language alters large language model preferences. And alignment doesn't shift preferences or knowledge representation similarly across language. Another challenge to effective evaluation. All right. So finally, I know I've talked a lot about pre-training data and benchmark data sets. What does that really mean for how do we actually take that information and move it towards a clinically relevant evaluation that is informative for clinical scenarios? And this is what is really, really challenging in any aspect of medicine, not just large language models. So this is the challenge we have here is most of our current benchmark data sets, as I said, are multi-choice question answer data sets or machine translation data sets for which there are clear gold standards here. There's only one right answer, and you can automate the evaluation because you can calculate the accuracy for question answer tasks. However, our highest value real world applications are much more open-ended and generative in nature. So one way that people are using large language models in the clinic is for patient portal messaging. So this is an example of a question that a patient might ask. This is an example of a patient with prostate cancer asking about who's experiencing uh, side effects of their hormone therapy. For these types of applications, the correct answer, there is no one right answer. It's a generative response for which many people might disagree on what the best response is. And there's or very, very few gold standard data sets for these types of real world applications. And importantly, we do not have a way to reliably automate these evaluations. So the question that we don't know is to what extent current benchmark data sets translate to a model's performance in these high value real world applications. I would argue that the two studies I just discussed, uh, uh, tell us that there are real limitations in moving from a benchmark data set to a high value real world application. But they could point the way into what are ways that you might take a task and alter it to probe risks that you're specifically concerned about. So you might take your kind of task of interest here, patient portal messaging. If you know that models are not robust to lexical variations, you could rewrite this or paraphrase it in various ways. If you know that a language model is likely to have learned a biased representation of a biased or incorrect knowledge representation due to inaccuracies or just statistical anomalies in their pre-training data, you can specifically then target those in your evaluations for your real-world applications. And this is, again, it's an example of just to highlight just how hard it is to do a high quality evaluation of generative output. So this is a GPT-4 response to the question that I previously showed from the patient asking about what their side effects are due to androgen deprivation therapy. You can see this is a long response, and this is for which many people would not agree on what the best answer is. There's no one right answer. There's multiple responses that could be correct. And this is a core challenge in NLP broadly. Language model is subjective and ambiguous. And at present, there's no way to reliably automate evaluations of these types of output. If you have a human written gold standard to compare against, there are some automated text similarity metrics that exist, but they will not reliably tell you about differences in clinically relevant output. So this is a real challenge right now. We can't automate this evaluation at scale, which uh, complicates ongoing monitoring if we move methods into clinic. To partially address this challenge, we've worked on a tripod LLM consensus reporting guidelines for transparent reporting of large language model research. It's modular, so there are different questions that apply based on your research design and your large language model task to account for the very generalist nature of many large language models. And it's a living document because this is a very rapidly advancing field. We wanted to get some usable consensus guidelines out there sooner rather than later to improve transparency and reproducibility, but acknowledge that things are rapidly changing and we want to have them be able to nimbly adapt as we identify new areas that could benefit from more robust evaluation. But our main what one of the key focuses of the tripod LLM checklist is transparency and reproducibility into data sets, the implementation, and most critically, the evaluation. One current, beyond just the technical limitations of our ability to automate evaluations of language model output and our ability to anticipate risks, is that we don't have a widely accepted framework by which to defining what qualities need to be evaluated for any given application. So especially now in early days, clear descriptions of how a large language model evaluation is taking place, how they're being scored by humans, if output's being scored by humans, and clear definitions of what is meant by a high quality output is really important to understand the risks and roles of language models at this point. And finally, I'll finish on the complicated challenge of evaluating evaluating how humans interact with large language models, which is how most language models are going to be implemented in clinic in the near future. So we did a preclinical study where we wrote 100 scenarios of cancer patients paired with questions asking about new symptoms that patient's experiencing. We were motivated by the fact that many EHR vendors were very early on excited about integrating large language models into patient portal messaging as a way to improve clinician burnout, which is promising, but needs to be evaluated to see if it actually helps and to understand the risks. So we simulated that in this setting. We first had 6 oncologists manually write responses to those questions. Then in our second stage, we had GPT-4 draft a response to those questions, and then had 6 oncologists edit the draft until they felt that it was appropriate and safe to send to a hypothetical patient. And what we found, we asked the physicians about what they thought about the quality of the GPT-4 drafts. And physicians thought the drafts were acceptable without edits in 58% of cases, which this is a little bit how whether you're glass half full or glass half empty type person. I was pretty impressed by this because GPT-4 is not an oncologist. And they were associated with a low risk of harm if they were not edited in 82% of cases. However, in a small but clinically, if translated, a significant minority of cases were associated with the severe harm or death if the drafts were left unedited in 8% of cases. And we found evidence of automation bias and over-reliance that could expose that risk to patients if physicians don't catch those errors. And this, importantly, could disproportionately impact vulnerable group because one avenue that people are excited about using large language models is to help improve accessibility, which might mean that more vulnerable groups with less access currently are kind of interacting with more semi-automated systems than less vulnerable groups. So this could widen disparities if we don't study and control for it. This is where one thing, where we saw the potential value of large language models, though. This is the same question about a patient with side effects of their androgen deprivation therapy. Here now I'm showing the physician written message from that study. It's very short to the point, it's right, but not very detailed, versus the GPT-4 assisted message. And the GPT-4 assisted message includes a lot of really nice kind of description of the mechanism of action of androgen deprivation therapy and why that's causing hot flashes and night sweats, the symptoms that the patient's experiencing, and some conservative self-care measures that were good enough that the physician thought wanted to keep in. And a busy physician would never have time to include this level of detail in a patient portal message, or almost never have time to do that. So this is really promising, this educational content. But that did mean that the content of the responses were significantly different between the manual responses and the GPT-4 assisted responses, which is, reflecting anchoring and automation bias, which we often see with automated processes. So we reviewed all of the responses generated either manually in blue, the GPT-4 drafts, which are in red, and the GPT-4 assisted responses, the drafts that have been edited by a physician in green. We reviewed them for the content, the topics that showed up in the responses, so we could see how different, the final product is when you use our standard manual approach versus LLM assistance. And what we saw, these are the different content categories that we identified. The GPT-4 assisted responses were very similar to the GPT-4 draft responses in terms of the distribution of content in the responses, but significantly different than the content of the manually written responses. So the physicians do really change what shows up in the responses when using automation. That's not surprising, and it's okay as long as the final response is deemed to be safe and acceptable. However, as we gain trust and we get more used to working with the systems, clinicians might begin to over-rely on the assistants. And if we don't build in mechanisms and education to remind physicians to carefully review responses, errors could make it their way to the patient because as we showed, GPT-4 does have a small rate of dangerous errors that if they're not caught before it reaches a patient, and we can never expect the language model to have no errors. We can't expect it of any system. Interestingly, a few months ago, some of the earliest clinical pilots of using GPT-4 assisted patient portal messaging came out. And while they didn't look at this human computer interaction piece, they did look at task load and time savings. And what this came out of UCSD, and what they found was that although using GPT-4 assistance reduced task load, so was less cognitively burdensome for the physicians than writing a response manually, there was no difference in the time needed to arrive at the final response sent to the patient. So no time savings. So this is really surprising. I was surprised when I saw this when I read this study that even what seems like the clearest clinical benefit, when you integrate it into the kind of complex clinical workflow, we may not see what we anticipated to see, and we may not even see what we measured preclinically, highlighting the importance of real clinical evaluations of these new innovations. So, in conclusion, large language models have really rapidly advanced and generate some general stabilities in the biomedical realm. Benchmark evaluations don't tell you the whole picture of a language model's capabilities and might really overestimate their abilities. For the clinical workflow, language model risks extend beyond model performance to algorithmic bias, automation bias, and over-reliance. And there is a very urgent need for methods for preclinical and post-implementation evaluation to demonstrate the benefits and risks to the healthcare system, clinicians, and most importantly, to patients. So with that, I'd like to thank my collaborators and funders, and hopefully I've left a few minutes for questions.
That was awesome, Danielle. Thanks so much. Really incredible work. Just because we have a few minutes, I'll kick it off really quick. Um, so often these models go through like a reinforcement learning with human feedback stage that can improve responses in a lot of ways, but also like has interesting side effects of like distorting the calibration if you ask for random numbers, for example. I'm wondering if you looked at how RLHF impacts some of the metrics that you considered here for the medical models.
Yeah, so we looked at that when in the cross-care project, we compared the knowledge representations for the base models versus RLHF tuned models, version of the same models. We had looked at a series of models, including Llama. We couldn't use Claude or GPT for this study because we can't access their logins. Um, but we used Llama. And so we showed that RLHF and uh, uh, when you ask those questions, when you query in English, did shift the representations of the knowledge's kind of internal knowledge of what a demographic group is most likely to have a disease, but only in English. It didn't shift it when you prompt in other languages, probably again because those data sets are in English, which is pretty interesting. But I agree. I think the preference tuning that's used, um, we should be studying how that shifts knowledge and how that injects. But the idea, well, it might make the model more helpful. How that might uh, inject new risks.
There's a saying, questions elicit answers in their likeness. And I feel like it's been very true of LLMs, where like the way you phrase your question really can change the type of answer you get. I wonder if you think there's like how much benefit is there in sort of pre-processing prompts so that, for example, you replace brand names with generics, or do some kind of medical white glove prompt cleaning up before handing it to the LLM.
Yeah, I think it's a great point. And it's one thing where I like a little bit in the back of my head, still wondering like, is this the fatal flaw of large language models? This kind of issue of robustness. So I think at minimum, if you're going to do anything clinically, you should always study try and do some probing of the robustness for your task. But we've always seen a lot of instability, and other people have always seen a lot of instability. So I think you probably anticipate you'll see some, and sometimes that's interesting in itself. And for any clinical limitations, ideally you would account for that with kind of the pre-processing data cleaning. Um, but what I worry about is, it's difficult to pre-process if for a lot of the clinical applications for that use any clinical data, it might require pre-processing EHR data, pre-processing EHR notes, and we don't right now have really good ways to standardize all of that information to make sure that, there's, you could try as much as you can to standardize structured data. We're fairly good at that in itself in healthcare. But especially once you start incorporating clinical unstructured text and context, it becomes very complicated to standardize. I think that's another really interesting area is are there other ways that we can make these models uh, more robust and reliable?
Totally. Well, thank you so much for the awesome talk. Any last minute questions? Do you have a minute or do you have to run?
I have a minute if people have more questions. And if not, I please feel free to email me and happy to talk offline as well.
Thank you so much.
Thank you.